So, any questions about anything? Yeah, I'll go over the solutions to the exam on Monday and post the video and the notes, etc. I was finishing off that proof at the end last time and got kind of panicked. I wrote a couple things that were kind of silly. The calculation, so remember we start with a function that's harmonic on the d plus side of a symmetric interval, a symmetric domain like a disk in the picture. It's a local theorem, so anytime you can stick in a disk like this, you can do this kind of thing. So the function we're given is harmonic on the upper half of that disk, and it extends continuously to the real line, and it's 0 on the real line. So vanishing on the real line is important. Then you can reflect the function across the real line and make it harmonic. And of course the reflection, if you think about the gradient, if it had a kink, if it was increasing from 0 going up, then it better be decreasing from 0 going down. That's why the z conjugate in there. That makes it a u of x comma minus y. That's important. Otherwise, there'd be a kink. So for there not to be a kink, that minus sign is important in the conjugate. Anyway, the calculation, that's easy. You could also do this by getting Anyway, the easiest way to see that you get a harmonic function in the bottom that's the reflection is just by using the chain rule and taking the Laplacian of minus u of x comma minus y. Two derivatives in y just spits out minus 1 twice, so it doesn't change the Laplacian when you do that. And so we have a harmonic function on the bottom. And last time I indicated the proof was the weak averaging property. Oh, by the way, the fact that u is vanishing on the boundary and continuous up to the boundary means that reflected thing is continuous on the whole disk. So that's something I meant to say here. And so another thing is that u vanishes implies so u is 0 on R and continuous up to R. Implies that the capital U there is continuous on the whole thing. So it's continuous on D plus. On D, on all of it. Okay, that's important. So if I want to use the weak averaging property on U, I need to know it's continuous. Okay. And so the last thing was to check the weak averaging property. The weak averaging property holds in the top half, D plus, because it's harmonic there. It holds in the bottom half, D minus, because it's harmonic there. And then the only place I need to check where it holds is on points along the real line. And if you think about, think about a disk going around here. I need to check the averaging property on a disk like that. Well, at the center there, it's 0. So I need to see that the average on that thing is 0. And that turns out to be easy because if I look at the value here, it's minus the value of what it would be here. So if I pick a point, here's a z. Oh, let's see, that would be z bar. Here's a z bar. Here's the z. I've got u of z on the top, and I've got minus u of z bar on the bottom. So the integral on the top half cancels the integral on the bottom half. So the averaging property at x naught and r, the top half integral cancels the bottom half integral. and a 0, which is the value of the function at that spot. So check. The weak averaging property implies and U continuous, of course, so it's harmonic. And if you go back and look at the Schwartz reflection principle, look at the extension I showed you of the analytic Schwartz reflection principle. Go back and look at that. And when you do that, you'll get this. Let's say this is a real analytic curve. So we'd have a gamma here, which is a real analytic curve. Then we were able to map that real analytic curve by an analytic change of variables to a segment on the real line. And when you look at it like that, you realize if I had a function that's harmonic on this side, let's call this D plus, then there'd be a weird shaped thing here because the change of variables would be an actual disk. So over here, I'd map to the real line by a change of variables. Maybe I shouldn't make this a disk. I should make it something weird. This is the disk side. And I would pull this back when I do the change of variables and get a weird shaped thing maybe that's not a disk. And on this side would be something that's also not a disk probably. It wouldn't have to be symmetric either. So I made a weird bulge there so it's not symmetric. Anyway, the fact is, if U is harmonic on D plus, continuous up to the gamma, and 0 on gamma, then U extends harmonically past the curve. So whenever you have a real line Schwartz reflection of some kind, you get one for real analytic curves because you can change variables via an analytic function and pull back the theorem. So past gamma, which means what it means is if I have a point like this right here, there'd be an open set where it extends harmonically to that open set. And you get it by pulling back that little disk that you could do the Schwartz reflection principle on here. And we know that analytic changes of variables preserve harmonic functions. So this would be a one-to-one onto thing. Have an analytic inverse, etc. Anyway, that's just a remark. So, the Schwartz reflection principle sounds incredibly special, but it has this generalization to a much more general kind of thing. Questions about that? Well, we've kind of been tiptoeing around a more general Cauchy theorem. When I did the Cauchy theorem for the annulus, you could have guessed probably that that can be done in much more generality than just the annulus. So here's the general Cauchy theorem. I'll first give you the feeling for it. Let me draw a picture here. Oh, let's have something that's analytic on a blob. Let's make it have 3 holes. Okay. So F is analytic on that blob. The outer boundary I'm going to make go around counterclockwise. Let's call that gamma 4. And the inner boundaries, I'm going to make these curves go, they're slightly inside. These are going to go clockwise. Let's call that one gamma 1. This one gamma 2. And this one is gamma 3. Okay. And I want to get a Cauchy integral formula out of this. Let's pick a point here, A. So here's the feeling for a general Cauchy theorem. Feeling. I look at that picture and I realize I don't have a simply connected domain here because I got those holes. But if I cut the thing up, I could get a simply connected domain. So for example, if I look at, I could cut it in half, top to bottom. Then the top half would be simply connected and the bottom half would be simply connected. Okay, and if I made slits here, let's see, I'll go this way on the top, this way on the bottom. Make a slit going here, this way on the top, this way on the bottom. So they cancel, etc. Let's see, I got to go this way. Yeah. Then you'll notice if I do a top half there and have the purple slits going that to the right, I get a simply connected region up there, and I get a simple closed curve in a simply connected region. The Cauchy theorem would tell me that integral around that thing is 0. And then similarly on the bottom half, I would get the integral around that thing is 0. And when I add them up, so here's the feeling. This is a notation. Gamma is equal to the union as k goes from 1 to 4. So in other words, just toss them together of the gamma k's. That's called a chain. It just is a, what is it called? I guess it's called a cycle in some books, or a chain. You just string curves together and call it a chain. And that's if you string things together which are just curved segments. It's actually a cycle. It's called a cycle in the topology world when the gammas are closed. So those are just words for that. And we will write the integral along gamma of f dz is the shorthand notation for the sum as k goes from 1 to 4 of the integral along the gamma k's of f dz. We'll also write the index of with respect to gamma of the point A is 1 over 2 pi I integral around gamma of 1 over z minus a dz. And that's just a sum of the indices of the gamma k's of A. Okay, so that's just notation. Well, our standard Cauchy theorem when you eyeball that picture, you got a simply connected domain on the top and a simply connected domain on the bottom, and I've got a closed curve inside a simply connected domain in those cases. We see that the integral around gamma of f dz is 0. Because when you add up the top half and the bottom half, the slits cancel. The slits cancel, leaving capital gamma B. Also interesting, if I do the Cauchy integral formula, so here's an exciting fact. Apply to, instead of f, do it to f of z over z minus a instead of f. The top half would give me f of a in the picture. Remember my a is, I put it in the top half. The top half would give me, by the Cauchy integral formula, the f of a, and the bottom half would give me 0. That would equal f of a. The bottom half would be 0. And if my a was on the slit, I would just move my slit a little bit. Bottom half equals 0. And so we have a Cauchy integral formula, which is a general Cauchy integral formula. F of a in that picture is 1 over 2 pi I integral around a gamma, if I choose the proper orientations, of f of z over z minus a. So that's an exciting way of thinking about a more general Cauchy integral formula. Let's see. Now, so people realized they could do this, and when they had some explicit thing to do, and they were trying to figure out, okay, what should the general theorem really be? And of course, that took some years to realize what the hypothesis should be for the general picture. And they finally came up with this thing, which is a topological concept, which I'll explain in a minute. So that's just the feeling. I'm done telling you about the feeling. Now there's a fact I need to mention. Fact. Index gamma with respect to A is a constant. It's constant on connected components. Connected components of C minus the trace of gamma, which you guess what the definition of that is. It's the union of the traces. And in fact, it's an integer. unconnected components. Could be plus, it could be minus, could be 0. Okay, so let's see how, that's an easy thing to see. I guess I've shown stuff like this before. Why, if I take d by dA of the index, then that's 1 over 2 pi I. Remember, you can differentiate under the integral sign. And so I add up those integrals along the gammas, and I would get 1 over z minus a squared here. And since those are closed curves, if the gammas are closed, that's going to be equal to 0. Because that's the integral of a derivative. So, of course, that I can't differentiate if A is on in a curve. But if A is off of a curve, that's 0. And so when you look at the connected components, you've got an analytic function of A whose derivative is 0. So on each of those components, it would have to be constant. So the index is constant. Of course, it might be different constants on different components. We know that happens because when you take a unit circle, the index is 1 inside and 0 outside. And of course, it's not even it's not differentiable on the curve, so you can't talk about that part. And we know. So how would I know it's an index? It's an integer. Some books make a big deal out of proving this. My proof is when I did the argument principle. I showed you that it's the number of the winding number is the number of times you spin around, and I did that by looking at the argument and realizing when you come around, you come full circle, but you might have gone around multiple times before you come to that point that's full circle. And so the argument principle consequence using f of z equals z minus a. Shows that those things are integers. The index gamma k a is an integer. I've talked about that before, so I'm not going to talk about it again. Okay, so here's the big hypothesis for the General Cauchy theorem. Gamma is a cycle. Meaning gamma is a concatenation of where the gamma k's where the gamma k's are closed curves. They could cross each other, etc. We have an omega. So gamma is a cycle, and here's the new property. The index with respect to gamma of A is 0 for all A in the complement. C minus omega. That turns out to be a topological thing. And it's pretty interesting. It's amazing that, it's written in terms of analysis, in terms of integrals and stuff, but it's actually a very topological property. And it's one of the great things about complex analysis. You figure out these analytical things to write down that have topological implications, and it makes proofs analysis instead of topology. And sometimes those proofs are easier. This is one of them. Okay, there's a word for this. It's being homologous to 0. We say gamma is homologous to 0 in omega. And when we'll write this, we'll write gamma is homologous to 0. Or sometimes, if we want to emphasize there's a domain gamma omega in the background, I'll put a twiddle sub omega. And so the feeling I can deform gamma to a point in omega. So it's kind of like the feeling of simple connectivity, but of course this is not a single curve. It's a bunch of curves. And so how would I deform gamma to a point in omega? So I'll put that in quotes since I haven't told you what that means. Okay, so here's I have my this thing that I did in the beginning was homologous to 0. I'll make 2 holes. Okay, so how would I deform this down to a point? Well, I would start making these get a little bit bigger. I'd make this one get a little bit bigger. And then, let's see, at some point, they're going to touch. Let's see. Yeah, so I make little curves like that. And then I'm going to make, let's see, I'll make a cut here and go, oh, this is not good. Let me move these a little bit farther apart. Okay, so first I'll start out moving those out a little bit, and then I'm going to add a cut here, and I'll go this way like that, and this way like that. Okay, so I just at this instant I add that cut, and then I start going like this. Imagine a whole bunch of intermediate curves, and adding a slit doesn't change the integrals when it goes back and forth like that. They cancel. So those integrals would be constant, whatever they are, if it's an analytic function, by homotopy, and then I keep increasing that. And notice it's going clockwise. I keep increasing it until I get out here and realize, aha, I'm heading toward a curve but I'm going the other direction. So in fact, they'd cancel each other. So that's how you would do, you take your original curves and you're allowed to deform them and add slits and gradually move out until you get a curve that cancels the original. And so that's what it means to be homologous to zero. Of course, that's a very complicated topology thing to even say. And I don't think, but this thing is an analytical version you don't have to think about very hard. You don't have to draw pictures. So let's see, why is that homologous to zero? The index with respect to this, let's take this point in here. The index with respect to this one is +1, if I stuck a point in here. And the index with respect to this curve would be 0, because it's outside. And the index with respect to the outer curve is -1. So that'd be 1 plus -1 inside here. This one, same reasoning. This one, this curve would give me +1. This curve would give me 0 if my point was in there. And then this other one would give me -1. So 1 plus -1 is 0. And then the last place to check is out here. And then, of course, none of those curves contain this point. So they'd be 0 plus 0 plus 0. So this is homologous to 0 in my original picture, where I had that orange region with the holes inside the curves in the middle, on the inside. Anyway, the General Cauchy theorem, I guess I'm going kind of slow today. I'll probably make a 2-day lecture out of this.
I have a quick question.
Yeah.
What about points inside the big one but not in the two smaller ones?
This is about the complement. The A's in the definition are exterior to my omega.
Oh, I see.
Yeah, so I don't have to check anything that's inside omega. So the A's here, the A's in here, A's out here, A's in here are the ones that are outside. Yeah. So the General Cauchy theorem, omega is a domain in the complex plane. Gamma is a cycle in omega that's homologous to 0. Then 1, I didn't say F is analytic on omega. F analytic on omega. Then 1, the integral of f dz is 0 around the cycle, which is just the sum of those integrals. And a new Cauchy integral formula, and this really is new, f of a. There's a new thing in the Cauchy integral formula, times the index of gamma with respect to a equals the Cauchy integral formula. 1 over 2 pi I integral around gamma f of z over z minus a. And that's whenever a is in gamma minus the trace of, it's in omega minus the trace of gamma. So not on gamma.
Can we give an example of a curve where the index would not be 1?
Yeah. Let's see. Here's a note. Yeah, so an example. The cycle I chose in the beginning to give you the feeling is the best, most natural cycle. It's the simplest one, homologous to 0. And that's when the index of the points A inside would be 1. And so that it's nice and simple. In fact, it's called a simple cycle because it has an inside and an outside. The inside is where the index is 1, and the outside is where the index is 0. And there's only one spot where that one component has index 1 and all the rest have 0. That's called a simple cycle. But here's a not so simple cycle, I hope. Let's have a region with one hole, and then I could have the outer cycle could go around twice, and it could go, I don't want to, am I going to get too carried away? That one went around twice. And let's have this one go around twice this way. This is going to get hard to look at. I'll make it go around twice. Let's see. And I can make it go around like a figure 8. Oh. I'm going to make it go around like a figure 8. And then I'm going to go around twice. What a mess. Okay. Anyway, yeah, that's too much. How could I make it look like? I'll make this one go around twice that way, and then I'll have one over here that goes around that way. Or does it? And does anything? It could make a figure 8 here. Okay, if you think about the index here, that would be plus 2 would be the outer one because it goes around twice, and minus 2 would be the inner one because it goes clockwise twice, and the other one's irrelevant because it's outside a disk, and so the index with respect to that one would be 0. So it would be 2 minus 2 plus 0. That adds up to 0. And out here, they're all 0. So let's call this A1, A2. At A1, the sum of the indices is equal to plus 2 minus 2 plus 0. A2, the sum of the indices is equal to 0 plus 0 plus 0. And that's all I have to check. So they can cross, they can do all kinds of weird things. Okay, this is I'm going to give you a very simple proof. I'll probably just get it started today. It's amazing how it took years for this simple proof to be figured out. If you look in older books, like Konrad Knopf, he made this theorem rather excruciating in a more general case by doing it with his bare hands and having rectangles and partitions, and it's a mess. And so this is a very clever proof. Alfors used to attribute it to, let's see, when I took this class back a long time ago, they didn't have this proof in the books yet. And in the third edition of Alfors, this proof got added. So Alfors attributes this snazzy argument to Bearden, and Stein attributes it to somebody else. So I don't know what the true story is. I should look it up and see. Anyway, Stein has it in there too. Okay, it's a clever, sneaky proof. And here's the trick. I'll call it a trick. In fact, there's going to be tricks which are very clever and make it simple. And one is to have a function of two variables, which is the difference quotient. f of z minus f of w over z minus w. So we're doing several complex variables here. It's exciting for me. Now let's see, that's when z is unequal to w. Where the z and w are in omega. And when z is equal to w, of course, it should be the derivative. I'll pick one of the, pick z, when z is equal to w. Okay, step one is to show that G is continuous. G is continuous as a function of two variables on omega cross omega. Of course, it maps omega cross omega into this complex plane. Well, that's clear when z and z naught are staying away from each other. So it's clear at z naught, w naught, where they're different. So I only need to check continuity at z naught comma z naught. Okay, so here's how I'm going to do that. Let's say here's the picture. Here's a disk contained in omega, whose closure is contained in omega. Why not? Omega's open, so I could cook up a small disk like this. And now I'm going to take a z and a w that are close to that. All right, so let's have a z and a w that, let's make this be a w and this be a z. And let's call this, I'll make this the line that connects those two. Starts at w and goes to z. And so let's think about g of zw minus g of z naught z naught. I won't put the absolute value, the modulus yet. That's equal to f of z minus, that when w is not equal to z, this is the difference quotient. Okay. And we've kind of seen things like this when we differentiated integral signs before. This, that f on top would be the integral from L of f prime of f prime of zeta d zeta. Okay, how can I make that other thing look like that? Well, if I integrate a constant, let's see, a great thing, this is the integral of, if I integrate a constant, d zeta, it spits out z minus w times the constant. Constant. And the integral would be equal to the constant times the z minus w. And that would cancel the z minus w in the bottom. And now you realize I see where I'm going to get continuity from. Those two integrals on the top are really close together. So close together that when I divide by z minus w, it doesn't matter. So, the modulus of z integral zw minus g of z naught is less than or equal to 1 over the modulus of z minus w times the integral along the line of f prime of zeta minus f prime of zeta naught, z naught, d zeta. And by continuity, let's see, we know the derivative is continuous because analytic functions, the derivatives of analytic functions are always continuous because f double prime exists. So let's see. Let's make this, well, I guess I'll make it. This is less than or equal to 1 over z minus w. I guess this is an equality. This is less than or equal to the max along the line of f prime of zeta minus f prime of z naught and times the length of L. And that's what is going to cancel that z minus w. That's the scary thing. And I can make this less than epsilon. When what I need when that disk is small. By continuity of the f prime. And so that's how I get continuity. So that whole thing goes to 0 as the radius of the disk goes to 0. Okay, so let's see. We're going to see that, let's see. The next step, now that I've got that out of the way, is to define h of z, which is the integral in the other variable around gamma. So g of zw dw. The plan is we're going to show that actually h extends as an entire function, and it's going to be a bounded entire function. So I've only got a couple seconds here. I will show h extends to be entire, and it's bounded entire. That's easy to check. Bounded entire, so constant, and in fact it's 0. Constant, and the constant is identically 0. And that's going to give us the proof. We'll see that that's equivalent to the statement of the theorem. And the next thing is to show that h is analytic, and that's Morera's theorem. Okay, I fit that in the last 2 seconds. So